Okay, welcome everyone. Last time we started a new topic before the end. We started talking about greedy algorithms, and we said that this is a very powerful way to design algorithms for different kinds of optimization problems. And what they have in common is that they can be cast as a sequence of choices that we have to make. And we started by describing one such example problem, which can be phrased in that way, where we have sort of a sequence of choices. And we wanted to see if that's sort of if there's an easy way to solve this problem as a greedy algorithm. Actually, I'm not sharing my screen yet. Okay, and so this problem was the 0-1 knapsack problem. And we said that the idea is we have to, or the problem is that we have to steal a lot of valuable things, and we have to choose between diamonds and maybe a painting and other things that are of different weight and of different value. And the question is, what do we pack into our backpack, assuming that we have sort of knee problems and can't carry too much weight? What do we choose, such at the end, once we sell all the items, we sort of make the maximum profit in this case? And then we suggested one way to do it is to not just pick the most valuable item or the lightest item, but pick the item that has the highest value per pound. And so if you do this, we'll end up initially with the following solution. So here's our backpack, and it carries, or it has a capacity of 50 pounds, we said, right? And so the best item in terms of dollar per pound would be the smallest item here, which is worth $6 per pound. So we're filling this first into our backpack. We have this small item of 10 pounds. And we have 40 pounds left in our backpack. Which one would we pick next? We would pick next to the second most valuable per pound, which is this one here, and fill up another 20 pounds of our backpack. And so we have reached in total 30 pounds in this backpack. And you can see that's the last item that's left, the most valuable in absolute terms, doesn't fit into this backpack anymore. And so we have to stop here. And so this greedy approach, is very naive approach of picking in each step the one of highest value per pound. In this case, gives us a total value of this backpack of $160. Total value of this backpack would be $160. And you probably have already seen that this is not the best solution. Does anyone see what the best possible packing would be of our backpack? Yeah. 30 and the 10. Are you sure? Yeah, that would work. Let's say we have 30 and 10. You said. So this would give us a total value of 30 and 10, $180, which is better than our greedy solution. Yeah. But this is the best we can do, $180. $20 and 30 pounds we get combined. We still satisfy the 50 pounds limit, and we would get a total value of $220, which would be higher than this. Correct. So we would pack 30 and 20 pounds into our backpack, completely filling up the backpack and achieving a total value, in this case, of $220. So in this particular case, you can see that greedy gave us pretty much the worst solution. It's not only not optimal, it's really the worst in this case. So you can see it doesn't work always, and we need to be more specific with the kinds of problems that we should solve. We should be solving with greedy approaches. We need to have more structure and more properties that we sort of make compatible with such an approach. So here, just to summarize, and I'll try to, whenever there's no formula or no symbol, I think I will just try to type on my iPad. This is good for me and also good for you in terms of handwriting. And for me, it's better because it's a bit faster. So in this case, the greedy approach failed. And we need sort of another ingredient to make this greedy approach work. Okay. And so the second ingredient that we need is one that is very intuitive, namely that every time we pick an element, this element has to be part of some optimal solution. So in other words, as a counterexample, so to speak, in our case, if we did greedy, we started with the 10-pound item, and you can see that, I mean, there's only one optimal solution, I mean this one, and it doesn't contain 10. So in this case, this was not a safe choice in the sense that there is no optimal solution that will contain this item. And this is what we require from a problem that we want to solve using greedy. So this will be the second property here. This is called, let me do this also in red. This is the so-called greedy choice property. Simply says that we have to prove that there exists, make an exist symbol later, there exists an optimal solution that makes the greedy choice. So and this should be good enough, you would think. If in every step the choice that we make is part of an optimal solution, we should be good. But if you think more carefully, actually that's not necessarily good enough, because it might be that every choice that you make is indeed part of some optimal solution, but not of the same optimal solution. And so therefore, in the end, it might happen that you can't really put all these choices together to one consistent optimal solution to the global problem. And so let's write this here as a note, do not forget. So does everyone see that this is these are two different things? Sort of making a choice in every step that is safe doesn't mean that if you make a sequence of safe choices leads to an optimal solution necessarily. And this is simply because we require it's part of a optimal solution. But if it's part of different multiple optimal solutions, then you might not be able to combine it into one optimal solution. And as I said, this is what the 0-1 knapsack problem doesn't have. It doesn't have this greedy choice property, because as you can see that the item of 10 pounds is not part of the optimal solution, and we made this choice. So this was our problem here. Okay, so having said that, we need to have more than this. So we said we have a sequence of choices, and let's say that in every step we make the right choice, meaning we pick some element that is part of some optimal solution. So what else do we have to require from a problem to be guaranteed to end up with an optimal solution in the end? Okay, so this is going to be our third ingredient. Always red so far. And this is essentially describing exactly this property of being able to putting together all your choices into one consistent optimal solution. And this is called optimal substructure. The optimal substructure here simply means that an optimal solution to a problem contains within it optimal solutions to its subproblems. It's going to be a bit abstract, but I'm giving an example later. Problem has optimal substructure, or OS here for short. If an optimal solution to a problem means within it optimal solutions to subproblems. And in fact, knapsack has this property. If you think about, let's say, the optimal backpack that you could get when sort of breaking into someone's apartment, if you take out the most valuable item, then what's left in your backpack must be an optimal solution with respect to the remaining capacity using the remaining items. Because if that wasn't the case, you could just swap that suboptimal packing and put your most valuable item again on top of it and get a better solution. So whenever you take something out, the rest must be also optimal with respect to the remaining instance. And therefore, in this sense, this 0-1 knapsack problem has optimal substructure. So it has optimal substructure, but it doesn't have the safe choice. And that's why knapsack didn't work, even though it has optimal substructure. Okay, so to summarize again, greedy approaches we can apply whenever we can cast an optimization problem as a sequence of choices that we have to make. And after every choice, we have to be left with one subproblem at a time that we need to solve. The second, and then we have two requirements such that we can guarantee that this solution will yield an optimal solution. A, every choice that we make in every step is optimal or is part of some optimal solution. And B, the sequence of choices I can in the end put together to an optimal solution to the global problem. This is this optimal substructure property. And so before I come to an example, we're going to talk about minimum spanning trees now, and minimum spanning trees is a nice example of a greedy algorithm that nicely describes these properties, and then it might become more clear. But since there was a question about Ford Fulkerson last time, so maybe based on this description now and these three properties, it's now more clear why in this terms, Ford Fulkerson cannot be sort of considered a greedy algorithm. In literature, very often the term greedy is very loosely used for any method that at some point is iterative and makes at each point like a very greedy choice in the sense that it tries to, for example, push as much flow as it can in each step. But in our case, we really said we want to have a greedy choice, but we want to be always left with one subproblem that we solve after making a greedy choice and never look back to our previous decisions, right? We said we make a decision and then solve the remaining problem, but put it together in the end with the choice that we made initially. So we never reversed the decision that we made initially. And so with the maximum flow, this is exactly what we tried initially. If you remember, we had our network, we picked a path from S to T, and we sent as much flow as we could from S to T, and in this way it's sort of greedy, even though we didn't really necessarily look for the one path along which we could send the maximum amount of flow. But even if we did, we saw in an example that this was not good enough because in each step we would find a path, push as much flow as we could until we couldn't. And then we saw in this example that we end up with a solution that wasn't optimal. And then we said, well, to fix this, we actually have to look at the residual network. And the residual network allowed us to essentially undo some flow. In this initial example, we had sort of an initial flow, and then we wanted to go backwards some edges and sort of revert some of the flow that we have previously sent along this edge. And this is sort of against this greedy idea that we send the flow. So we choose basically paths and flows in this case instead of jewelry and paintings. And we never undo this decision. So once we send a flow, we're done. But in Ford Fulkerson, the idea is that you are actually not doing this. After sending this flow, it might be that in subsequent iterations, we will undo some of the flow that you have sent in previous iterations. And in this sense, your decision in each step will depend sort of on previous decisions that you made, which you use in this residual network. This is sort of just a side note. But I'm sure if you Google greedy and Ford Fulkerson, you probably get a lot of hits. Okay, but I want to come to a problem that's called the minimum spanning tree problem. Again, a very popular and powerful problem that has applications in many different fields, including, again, computational biology. We are going to look at, or we start the whole thing with a different motivation or with a different application, so to speak. We're interested in looking at an atoll of islands in the South Seas. And let's say we have a bunch of islands and we want to, and you're the mayor of this atoll, the Takatuka land, and you want to come up with ferry lines that connect these islands. And you want to be able to really travel from any island in this atoll to any other islands. You don't care necessarily if you can do this in a direct connection. You don't mind going through other beautiful islands, but you want to be able to really travel from every island to every other island. And every connection, every ferry connection between two islands will cost you a certain maintenance cost, or you have to buy, I guess, a ferry and personnel. And so every connection will cost you some dollar amount. And the goal is to establish ferry lines between certain pairs of islands such that the total cost is minimized that you sort of save money by finding the right ferry lines. But in the end, being able to really travel from every island to every other island. So let me illustrate this with the picture. So this is called the minimum spanning tree. And here's an example. So the example, as I said, will be that we need to connect islands by ferry lines. And you want to minimize the total cost. Here's an example instance. Here is, in this particular case, 4 beautiful islands. And establishing a ferry line between these 2 islands would cost us 7 units of Takatuka land dollars, 2 units here, and maybe $3 here, $6 for this one, and $3 for this one, and let's say $4 of this one. Okay, and this is just for the record, the length. So if you look at this problem, the first thing we notice is once we're trying to pick a subset of these edges, or sorry, of these ferry lines, at this point we don't have any edges. We don't want to create any cycles in this sense. So if you look at this edge here, this one, I definitely won't have all these ferry lines in my optimal solution because I could, for example, exclude this one without breaking connectivity in this example. Connectivity meaning that I still can travel from every island to every other island. And that's simply because this edge is part of a or the cycle, namely this one, and removing an edge or a ferry line in such a cycle can never sort of break connectivity. If you take the endpoints of an edge that were part of this was part of a cycle, and the two endpoints will still be connected through a different path that doesn't include E, and that's how they form a cycle. So we can remove these edges, and so at the end of the day, what we're interested in finding is what's called a spanning tree, which is a tree in the traditional sense in graph theory. Did you learn about trees in previous lectures? Yeah. So a tree meaning that you're connecting all nodes. This is why it's called spanning. You try to span all nodes in your graph or all islands in your atoll. But without introducing any cycles. So this is an undirected, in the sense, you will see an undirected, connected acyclic graph, a tree. And so you're essentially looking for a spanning tree of minimum cost. Let me just name this. This is the spanning tree we're ultimately interested in. Spanning tree, because we don't want to have cycles, because they wouldn't really be helpful in this case. So now, more formally, we're interested in the following problem. Try to translate this Takatuka-Land problem into graph theory. Then the minimum spanning tree problem is as follows. So the input to this problem is an undirected graph. So this is representing our atoll of islands. Undirected graph G. Node set V and edge set E. And in addition, we're given edge weights. That we denote by WE for all edges E. And we do allow negative weights. In this particular example, it didn't make sense with ferry lines, but in other settings, it might help to be able to model this with negative weights. And so the output, what we want to compute in this problem, is a tree T. And tree T is defined on the same set of vertices V, but on a subset of the edges E prime, such that for one, E prime is a subset of E. So we're picking a subset of our original set of edges. And two, we do this in a way such that the total weight of that tree is minimized. And the total weight is simply the sum of the weights of all the edges in E prime. So E prime minimizes the weight of T, which we define to be simply the sum over all edges in E prime of WE. Okay, and that's a problem that we want to solve now using a greedy algorithm. Any suggestion you would, out of the blue, just come up with? How would you come up with how would you cast this problem as a greedy problem? How would you? What choices can you? What are the choices that you have to make? In this particular case, the choices are very natural. It's edges. It can include an edge or not. So which edge would you pick if you were greedy? Or which islands would you connect first? Any suggestions, ideas? Yeah. Exactly. And this is what we can do in every iteration, except that we have to be a bit more careful in later iterations. So every time we look for the cheapest remaining edge, but it might be an issue with doing this at some point. Namely, Exactly. So the edge might introduce a cycle. And that's why we say, well, let's take the cheapest, but the one that doesn't introduce a cycle. And that's the whole algorithm. And that's a greedy problem, or this is sort of a greedy scheme, because in each step we make one choice, namely which one to add. We do it greedily in the sense that we always take the cheapest. And once we do this, we sort of remove this edge and then make decisions on other edges. So we just sort of solve another subproblem. So here's a way to describe this. Second, let me write this again. Does this make it better or worse if I switch back and forth between writing and typing? Or you don't care really? Writing is better, yeah? Or is this like, yeah. I tried to write, but yeah, once there's like symbols and letters, I need to go back to the writing. Okay. So first, we need to cast this as a series of one subproblem choices. The idea that we had is to simply do the following. So this is what we would call typically a heuristic. Heuristic is sort of a scheme for which you don't really know if it's working. It can be just sort of a, not necessarily a clean algorithmic description with a performance guarantee, but it might or might not work. And we will see actually in this case it will work. So we add the lightest edge that doesn't produce a cycle. Okay, so this is an example. So let's say we have the following graph with nodes A, B, D, E, E, and F. And we have the following edges. 6, 5, 4, 2, 4. Two. One edge is missing. This one has also weight 4. Okay, so what edge do we start with in this case? Using this heuristic, adding the lightest edge in each step. I think the first edge is pretty clear. We take the cheapest because we can't introduce any cycle initially, which would be this one. Then we have an edge of weight 2, which would be this one. And we can introduce it. And which one would be the next edge that we would add to this case, to our current selection of edges? Any suggestion which edge would come next into our spanning tree? No? So what's the, yeah? Weight 3. And why didn't you pick the weight with weight 2? Sorry, the edge with weight 2? Exactly, yeah. Okay, so the next cheapest edge in this case would have been this one with weight 2, but it does introduce a cycle, as you can see here. And then so we skip this one and take the next cheapest, which in this case would be an edge of weight 3. Could take this one, and this would not introduce a cycle. And then edges of weight 4, we look at this edge, we can add it because it doesn't introduce any cycle. And finally, we have one edge left with weight 4, which would be this one. And it again wouldn't introduce any cycles. And that should be all we need to do. And this you can see is a tree, so it doesn't introduce any cycles. And it's a spanning tree because all nodes are connected or incident to one of these green edges. So this is why this is a spanning tree. And the weights of this spanning tree, if you sum up the weights of the green edges, they should sum up to a value of 14. So the weight of T in this case is equal to 14. So this is the solution of our heuristic, and by design, it will not introduce any cycles, and we only end once we span all nodes, so it's clearly a spanning tree. But one thing that we don't know yet is if this tree is actually the best tree, the best spanning tree in this particular example. Yeah. C to D, this one. The path from C to, you said D or? So B to T is 2, yeah, is 2. And what else do you say? Which path? Sorry, I don't see where you got the 7. So it's okay, the usual. This one? Yeah, that's a 1. Okay. Yeah, I forgot. Let me write this here. Any other question? And so now to show that what we actually get in the end is optimal, we need to show that the problem has these two properties that we mentioned before, that every edge that we're choosing is part of some minimum spanning tree, and that in the end we can everything put together to one global optimal solution, that this problem has an optimal substructure. So let's try to do that. Let's start with the second property, or the second criteria that we need to satisfy. So this would be that we have to show that the greedy choice property holds. Show greedy choice property. And for this, we need a few definitions that are very much similar to what we have defined previously, but just maybe also as a reminder what a cut is. So we defined ST cuts before, and now we're defining sort of more general cuts that are not defined based on any dedicated vertices S and T. And so for an undirected graph, we have G with node sets V and edges E. A cut is simply a partition of V. Okay, we split our node set into two sets, and these two sets are disjoint, and together they contain all nodes in V. This is what partition means in a traditional mathematical sense. Here's an example of a cut. So let's say you're given the following graph with 5 vertices, 1, 2, 3, 4, and 5. Then one example cut would be the following, and I'm using the same notation that we had used previously for an ST cut. So a cut in this case would look like this. We have one set of vertices that contain that contain 1, 2, and 3. And the other set contains the remaining vertices 4 and 5. So that's the notation we are using for cuts. This is exactly the same as we did for maximum flow. And now we want to relate cuts to subsets of edges. And we say that a cut respects a subset of the edges whenever these edges don't cross this cut. So these edges can lie on either side of this cut, but they can never cross this cut. And then we say that this cut respects a certain set of edges. Here's the definition. A cut S, comma V minus S, respect A, respects some subset A, subset of our edges, if every edge in A either every edge lies in S or every edge lies in V minus S. So either, and lie in S means that both endpoints are in S. So U in S and W in S. Or alternatively, U will be in V minus S and W will be also in V minus S. Okay, so no edge really in A crosses the cut between S and V minus S. Again, here's an example. We have again the same 5 vertices. And I will mark our edges, our subset A in blue. We'll have these 3 edges selected in A. Okay, so this is an example of a graph and a subset of the edges A. Then you look at this cut indicated here by this red set of vertices that contains 2 and 4. Does this cut into 2, 4 and into 1, 3, 5, does this respect our current set of edges A? Yes or no? Is it clear to everyone what it means to respect the set of edges? Or is it clear what the cut in the cut looks like in this particular example? Yeah. Yeah, the blue edges are A. No, it doesn't, right? Because a blue edge crosses this cut. So A, let me maybe mark this. So this is the blue edges are in blue. Sorry, the edges in A are in blue. And then the red cut does not respect this set of edges. And in contrast to this one in green here, this green cut which contains vertex 5 in S and the remaining vertices, the remaining 4 vertices in V minus S. This cut clearly respects A because all blue edges will lie in this case in V minus S. Okay, so now we have everything we need to formulate the main theorem that we want to show. Right again. Let's say that, as before, say is A is a subset of the edges or some minimum spanning tree. So now A is a not just any subset of the edges, but we are assuming that this is a subset of the edges of some minimum spanning tree of this graph. And now we take a cut S V minus S that respects that set A. It respects A. And now we're looking at the lightest edge, so that the edge with the lowest weight that crosses this cut. And then we'll see what we can do with it. So let E be the lightest edge that crosses the cut. Then, I'm afraid I have to write this. Then A union, the set containing E only, is part also of some minimum spanning tree. So take a minute to think about this claim or this theorem, because this is an important claim. It says that once you have a subset of edges that will be part of some minimum spanning tree together, not every edge by itself, but your set A is really a subset of some minimum spanning tree, it essentially tells you how to proceed. It tells you pick a cut, partition your vertices in a way that respects your current set of edges, and then simply pick the edge that is cheapest that crosses this cut. And then you can safely add this edge to your current selection of edges, and you will be sure that the resulting set of edges that increased by one edge will still be part of some minimum spanning tree. Not necessarily the same, but some minimum spanning tree will contain A union this lightest crossing edge E. Does it make sense to everyone? Yep. Very good. So we'll prove this because it's a very nice and very simple and visual proof. But for that, we need the following lemma. You remember what a tree is? You said you learned what trees are. Trees, the definition is just a graph, a connected graph without any cycles. And one way to characterize this having no cycles is by saying I want to have a connected graph that contains number of nodes minus one many edges. Just write this down. Not off. I hope this was autocorrect and not me. Delete this. Tree, if and only if the number of edges is equal to the number of nodes minus one. So we're not going to prove this. You can, in this case, look up the textbook, page 135. But it's more important, I think, or it's very, not more important, but it's, in this particular case, very easy to get an idea why this is true. So imagine you want to create a tree so you're given a set of nodes and you want to create a set of edges that form a tree. You start from an empty set. And let's say you grow this tree gradually. You start from one edge, and this one edge, the first edge that you will add, will connect two of these nodes. And then every time you add an edge to the set of nodes, you will connect one additional node to this current selection of nodes, until you have found basically, until you have connected all the nodes in your graph. And this will give you exactly n-1 many edges. And because you can't afford really introducing any cycle, so as soon as you're using one edge in one of this, in one iteration of this procedure to close a cycle, then the two endpoints would be sort of already being connected, and you will not introduce or reach any other additional node of your graph. So long story short, with every edge that you're adding, you can't afford closing a cycle because otherwise you won't reach all the nodes in your graph. So you need all n-1 many edges to reach these nodes, and you can't really close a cycle. And that's why this is basically the same as saying this graph doesn't have any cycles. Clear? Or any questions? So let's go back to the main theorem then. So we were using this property to prove the initial theorem that tells us how to proceed from a certain subset of edges of an MST. Actually, part of it I can type. So after this lemma, we want to prove the theorem from above. Okay, so we said A, the set of edges A, is a subset of edges of some minimum spanning tree that we'll call T now. Okay, so by the assumption, this is what the theorem assumes. By the assumption, A, the set of edges A is a subset of edges of some minimum spanning tree T. And then the question is that this lightest edge across some cuts, can we add this safely without making any mistakes? Yeah. Yeah, exactly. Yep. So now there's two cases. The easy case is, so if you look at this new edge now, the lightest edge across some cuts that respects A. If that new edge is already part of T, then there's really nothing to show, because then the statement of the theorem holds. If A union E is part of the same minimum spanning tree, the claim holds. So there's really, in this case, this is trivial, we don't have to show anything. So if E is part of the same tree T, then nothing to prove really. So it gets more interesting if E is not part of the same tree. So if this edge E is not part of T, then now we will construct a new minimum spanning tree T prime that contains this edge. And this is sort of the main task we need to do here. So if E is not in T, we will construct a different MST T prime that contains this edge. So we will construct a new minimum spanning tree T prime with E element T prime. So E, this new edge, will be incorporated in this new tree. So let me make a figure how this currently looks. So we have our cut S in V minus S. And we have a partial solution here. So we have some edges in A that will lie on this side. And we have some edges on the other side of the partition. But we won't have any edge in A that crosses this cut. And now let's say we're going to add this edge to our minimum spanning tree T. So this is the spanning tree that we're starting with, and T we said contains our set of edges A. Okay, so let's add an edge E, which will be the lightest edge. So by the construction of this theorem, we're interested in adding the lightest edge crossing this cut. And let's say this is this one here. So this is edge E. Then the crucial thing here really is to see that this edge will introduce a cycle in your minimum spanning tree T. And why is that? If I look at the minimum spanning tree T, which we assumed contains our set of edges E, will also have to connect this node to this node. The minimum spanning tree is connected, first of all, and that's why it's connecting also these two end nodes. But we said that E is not part of this T, so it connects these two end nodes by a different path. And this path must clearly cross this, the same cut, but through a different edge. And therefore, there will be an edge E prime somewhere in this cut in our minimum spanning tree T that crosses this cut. Okay, so we have introduced, by adding E to our minimum spanning tree T, we have introduced a cycle in this minimum spanning tree. Let me just write this down to keep up with that. So we add E to T, the minimum spanning tree that contains A, then this will create a cycle. Which is illustrated here on the right. And this cycle must have some other edge E prime that crosses this cut. Before everyone can follow, we haven't done much yet. So we just found one cut that is that respects our set of edges A, and we have added the lightest edge, and we see that this light edge will introduce a cycle in the original minimum spanning tree. And now I'm claiming that we can simply swap these two edges, and again we'll get a minimum spanning tree. So let's argue a bit more formally here. So the first thing to note is that the weight of E can be at most the weight of E prime, because we said E is the lightest edge across this cut. Okay, so since E is the lightest edge across the cut, we have that the weight of E is smaller or equal than the weight of E prime. Okay. And now let's look at the tree that we get by just swapping these two edges. So let's look at T prime. Be the tree that you obtain from T if you add edge E and if you remove edge E prime. So first of all, T prime is a tree. Anyone tell me why T prime is a tree. So which two properties do we have to check to see if T prime is a tree? Well, first of all, it has to be connected, right? And why is it connected? Because the only thing we did is we removed one edge that was part of a cycle. And we said in the beginning that doing so will not break connectivity. Right? If you take a cycle, remove one edge, the rest will still be connected. So after removing this edge, E prime, this will be still connected. And why is it cycle-free? Well, we said it's cycle-free if it has number of nodes minus one many edges. And since it was a minimum spanning tree before, and we just flipped two edges, we maintained the same number of edges. And if it was cycle-free before, it must be cycle-free now. And that's why T is a tree. So this is the one part, but of course we're interested in showing that this actually is T prime is not only a tree, but we want it to be a minimum spanning tree. So maybe just as a reminder, the main reason why this is a tree is because of the lemma above. Since we didn't change the edge count. But in addition, and this is the crucial thing about being a minimum spanning tree here, if you look at the weight of T prime, then the weight of T prime is equal to the weight of the original minimum spanning tree, T, minus the weight of edge E prime that we have removed, so minus W of E prime, plus the weight of the edge that we have added, plus W of E. And therefore, the weight of T prime is at most the weight of T, since we're adding at most as much as we have removed with E prime. Right, so, and therefore, the weight of T prime, right, is at most the weight of T. Can it be smaller? Can it be strictly smaller, the weight? Can the weight of T prime be strictly smaller than the weight of T? Yes or no? No, it can't, because T was a minimum spanning tree, so there can't be any other tree that is has less weight, and therefore we know that the weight of T prime is equal to the weight of T. And so the weight of T prime equal to the weight of T. That means nothing else that T prime is a minimum spanning tree. Questions about the proof of this theorem? So how does it help us really with this heuristic that we came up with initially? We said initially, in each iteration, we just take the cheapest edge that doesn't introduce a cycle. And now we have this other theorem that includes A's and T's and T primes and E. So how is this related? How does this theorem now help us in showing that our heuristic works in the sense that it gives us an optimal solution? Well, we wanted to show two things with this heuristic. A, that whatever we introduce is safe in the sense that this edge is part of some minimum spanning tree. And if you think about the heuristic in a way, at each step or each iteration, we have some partial solution of edges that we have picked previously, and we picked them previously without introducing any cycles. So we will have sort of a collection of connected components that won't have any cycles. And now, once we're picking the next lightest edge that doesn't introduce any cycle, the two endpoints of this edge must connect two of these not yet connected components. They're not connected because otherwise this edge would introduce a cycle. And now you can create a cut based on this that includes just one side of this edge, of this connected component on one side of the edge. And this cut is basically the one that you're picking the lightest edge across this cut based on this theorem. So let me make a picture. I think that then it becomes more clear. To link sort of these two ideas of the theorem and this initial heuristic. So maybe just to write this down, what we're trying to show here. So we are wondering at this point how this really helps us. And I will show you in a second the argument that I have just made, that it guarantees that the greedy choice, meaning the lightest edge that doesn't close a cycle, is part of an optimal solution. So here's the example. So here's your entire graph, G, and you're running this heuristic that we said before. And at some point, you will have connected some nodes, and you will have sort of these partial trees in your graph, and some nodes will not be connected to anything yet. And so now the next edge that you're selecting will look like this. You have an edge here in blue, which will be the next lightest edge. This is what we said. We always pick the lightest edge that doesn't close a cycle. And doesn't close a cycle means that it has to connect two of such components on both sides. So it cannot be part of the same components, because otherwise this blue edge would introduce a cycle. And then consider the following cuts. If I look at this cut, for example, which just includes all the nodes of the connected component of one side of this edge, and I could have also picked the other one, then this cut takes the role of the cut in our proof. And the blue edge will not only be the lightest edge in your heuristic, but it's also the lightest edge crossing the cut indicated here by this red set of vertices. And the theorem tells us that it's safe to include this blue edge because it will be part of an optimal solution, but even more, it won't be only part of an optimal solution, according to this theorem, but it's actually safe to add this to our previously added edges, and then the entire set of edges will be part of an optimal minimum spanning tree. So all this, what we have done so far, will lead to an optimal minimum spanning tree. If you keep on repeating this until we are all connected, we know that this set of edges that we have added all one step at a time will form in the end a minimum spanning tree. Okay, so this gives you the intuition. So this is the conclusion out of this. So we're not only showing that the greedy choice is safe because it's part of an optimal solution, but the theorem tells us even more. It tells us that the problem has an optimal substructure in the sense that we keep on applying this theorem, that we always will be part of an optimal minimum spanning tree. So at the end, when we are terminating, we have found a minimum spanning tree. So even better, It actually shows optimal substructure. Meaning, sorry. Each time we apply the theorem, we're guaranteed to be part of a minimum spanning tree. Simply by the claim of the theorem. And whenever we add an edge, we said that A with A union this edge will still be part of a minimum spanning tree. So at the end, this will form a minimum spanning tree. So when no more edge to add, we will have a minimum spanning tree. Okay, that's pretty much it. So let's write down the algorithm. This algorithm is called Kruskal's algorithm, this heuristic that we have just described. Crystals, man. So here's a bit of more pseudocode kind of description of the same heuristic. So let's call this Kruskal MST, which will be given a graph G, which we assume to be undirected and connected, and edge weights W. Then we start from an empty set A. So initially we don't have any edges in our minimum spanning tree. And we start by sort of creating a component out of every node by itself initially. So technically nothing much happens here, but we will let every node form its own set, its own connected component in the beginning. So for all the elements G point V, so G dot V refers to the node set of graph G. We call a function, and I'm naming this because later on we're interested in the running time, and then I can refer to these functions. We call a function make set of V, which will simply put this one vertex into a single sized set, so into a set of size 1. Okay, so this is nothing much has happened here except that every node in the beginning is its own component. In this figure here, you can see here we still have sort of these individual nodes that initially form sort of the singleton components. And then we sort the edges in a non-decreasing order because we want to start from the cheapest edge. So G dot E, the edge set of E will be G dot E sorted by or in non-decreasing order. By their weights, W. And then we go through all these edges in that order, in this non-decreasing order. Now we said GE. So whenever I write it like this is not super clean. If I write here this for loop over all edges in GE, I mean in the order that we have sorted it before. I'm not going to write explicitly again that we do this in the sorted order, but we first sort the edges and then we iterate over these edges in this particular sorted order. And then we check. And we essentially check if that new edge that you want to add, UV, will form a cycle. And we can do this by simply checking if the two endpoints of this edge are part of the same component. And if they're not, it's safe to add them. And if they are, we know it would introduce a cycle. Okay, so we simply check if the two sets are the same. The two sets that contain U and V will be the same. And for this, we introduce a function called find set. So if find set of U is not the same as find set of V, so meaning if there's two end nodes belong to different sets and therefore different components, only then I will add this edge to my current selection A. So this is the same as we said before. So in this case, only in this case, A will be equal to A union edge UV. And since we introduced this edge, we're connecting the two connected components or these two sets, and therefore we have to merge these two sets to one set or connect these two components to one component. This is what we did here. So once we introduce this blue edge here, these two components become really one connected component. That's why we have to call a function that we will call here in this context union of U and V. Okay, and then when we're done here, we're simply returning set A. So let's go through one quick example and then we're done for today. Here's a slightly more complex graph. A, B, E, and we have vertex D and F. E will be here. We have a vertex G. And finally, vertex H. Weight 1, 2, 14, 7. Okay, so this is our input graph. We have weights on these edges. So let's run this algorithm one through. We start with the cheapest edge that doesn't introduce any cycles. So in this case, it would be the edge of weight 1. Initially, C and E, the two nodes, are forming their own sets. So now after adding this edge, we will create one set that contains both C and E. We go to the next cheapest edge, which will have weight 2. So we're connecting H to a component that already contains C and E. Now this will form a component with 3 vertices. We continue with this edge of weight 2 between F and D. And you can see this is sort of forming this partial solution of a collection of connected components that don't contain any cycles. There's no edge of weight 3. So let's take an edge of weight 4, this for example, and here's another one of H4. Then there's no edge of weight 5. There is a edge of weight 6, but as you can see, we can't introduce this edge here of weight 6. It would be the next lightest, but it does connect 2 nodes that are part of the same component. So in this if clause here, we would find out that the sets that contain F and that contain E will be the same, and that's why we don't introduce this edge. The same for this edge of weight 7. We won't introduce it because it would connect 2 nodes of the same component. And we keep on doing this. Here we find another edge of weight 7. And this should, no, there's one connection missing. So we then have an edge of weight 8 that connects the remaining 2 components. So you see that this here at this point, we have two connected components that are disconnected from each other. And so the final edge will be this one that connects these two components. And you see that this forms a spanning tree. And but by whatever we have, but all that we have shown now, it's not only a spanning tree, it's actually the minimum spanning tree. This should be the tree of the minimum cost, the minimum weight. Yeah. Probably because of some handwriting. Can you say again, between? A2s. You could, you could do the same. It's the same thing. Yeah, you could have, I mean, you can swap it. You can see if you remove this edge and include this edge, it should still, it still forms a tree. So it's still connected. It doesn't have any cycles and it will have the same weight. Yeah, so whenever there's two edges with the same weight, you can actually choose which one to include on your safe side. Any other questions? If not, then see you next week. Yeah.
So BFS also has the optimal substructure property, right? I remember we discussed it in the previous lecture. So I think would BFS also have this optimal substructure property?
What are you trying to optimize with BFS? I mean, BFS, if you're okay. So not just traversing the